We're good? All right. Oh, awesome. Okay. So my name is Jonathan Kuskos. Welcome, first of all. This is an awesome venue, being in Rome finally for AppSecEU. This research is going to be a little different than most top 10 lists you might have seen in the past, mainly because this is chosen by us, by the information security community. And I'll get into a little bit of that here in a moment. This research was performed in conjunction with White Hat Security. Jeremiah Grossman has kind of been his brainchild for the last 10 years. 3 years ago, he passed it off to myself, and here I am, here to give this lovely information to you guys today. So what this talk is going to be a summary of the top 10 web hacking techniques that was decided in the beginning of 2016 for the year of 2015. Now, what we do here is we actually poll the InfoSec community themselves, like through Twitter, through mailing lists, et cetera, and we say, hey guys, what was the coolest stuff that you saw last year? What was the most important to you? What was the coolest research? And we're going to look at a lot of stuff. We're going to look at potential for widespread abuse, impact, overall pervasiveness. Obviously, highly technical research is going to be favored. So we'll get around between 50 to 100 submissions from that, from the people, and from anyone that submits something. And we try to vet it for it being obviously web app specific, being a web hack talk. Then once we have that, we trim it down. We have them vote on getting that to a list of top 15. From top 15, we then poll a panel of well-respected security experts throughout the world in order to order those 1 through 10, what is the most awesome hack, basically, down to number 10. And then once that's done, this talk will then, what we're going to do is we make a blog post about it, and then I kind of transform it into a talk where we can go through all 10 of those in an hour. Now, each of the 10 topics in here are absolutely worthy of their own 1-hour talk, and I'm going to attempt to squeeze all 10 of those subjects into a 40-minute presentation. There's going to be a lot of information here. We're going to be going very fast. Feel free to ask any questions along the way. Ideally, it'd be best if we could save them for the end, though, so we can just put them all together. But without further ado, let me actually start with what the old ones used to be. So going back in 2007, we're starting off with cross-site scripting vulns and common shockwave files, going on to GIFR vulnerabilities, creating a rogue CA certificate, padding Oracle crypto attacks, which we see all the time now. Then we start moving into a little bit more of TLS vulnerabilities, beast and crime. In 2013, mutation cross-site scripting became pretty prevalent, which is a new fourth type of cross-site scripting, like reflective, persistent, stored, DOM. And now we have mutation, which is where the browser is basically going to change good input into bad input and get past filters. And then last year we had Heartbleed, which we all saw all over the news. Without further ado, this year's top 10 list, as I showed, with number 1 starting off with the freak attack, factoring attack on RSA export keys. Now, like I said, all of this is very in-depth content. I'm going to try to just skim through it and give you exactly what you need to know as far as how to exploit it, how to remediate it, and that's that. If you're a security professional that finds it a little difficult to stay up to date with what's currently going on, this should be this should be a great refresher, basically, for what was hot last year, and then feel free to dig deeper if you would like to. So what I'm going to do here, since we only have 40 minutes, sadly, I'm going to skim through 10 through 6, just give you the basic highlights of that. And then when we get to 5 through 1, we're going to do a bit of a deeper dive into that. So number 10, hunting asynchronous vulnerabilities. This is by James Kettle. You might be familiar with the name because he's the head of research for Portswigger Web Security, which puts out the very popular burp proxy suite, which most of us in here are probably prevalent with. And in this talk, what he's going to do is he's going to go through a few concepts, such as finding functionality that is in fact vulnerable, but you might not know about it. Like sometimes you'll get a persistent injection in place, but you don't know that it's actually fired because you don't see any sort of output on your screen or anything calling back to you. This is kind of where Burp Collaborator came about. Because basically you have to do some sort of callback on that injection and wait for it to call out to you. Now, number 9 is by Robert R. Snake Hansen. He runs the popular hackers.org website way back in the day. This is about magic hashes. And magic hashes centralize around the difference between the double equals operator and the triples equals operator. Has anyone ever seen a difference between those? Does anyone not understand why you should use one or the other? A couple hands? Okay. So if you consider password hashes in PHP, they're base 16 encoded. And they can come in the form of 0E and then a series of digits past that. The problem with the double equals comparison there is that PHP is actually going to interpret that to be an integer and not a string. So it'll treat it as like a floating point value. Now, if you look at this chart here, and it might be a little tiny to see on the right side there, this graph is a list of hash types that, when hashed, are some form of 0E and then digits, which is going to equate to 0 when magic typing using the double equals operators in place. Now this is going to mean that if you have a password and you hash it, it starts with 0E. As an example, it's always going to appear to match the strings here, regardless of what they actually are, if the following are all numbers. Now the implication is that if these numbers are hashed and evaluated to 0, when compared against hashes, the comparison is going to evaluate to true. So this would be true for, like, say, evaluating password hashes. So you wouldn't need to put anything correct. You would just need to put in something that would evaluate to 0E and then some form of numbers. PHP is going to interpret the string as an integer. Now to find these values, what Arsenic basically did was just iterate over a series of incremental values, hashed it, looked for the value was this, did it about 1 billion times for each hash type, went through probably about, I think, 60 or 70 different hash types. If he didn't find one within 1 billion hashes, he simply moved on to the next one. And thankfully, the patch for this is pretty simple. If you're a user, you just use a password with high entropy. If you're a developer and you need to patch it, it's all about just switching the double equals operator to triple equals. And conversely, if you're doing the negative of that, not equals to not equals equals. There's also a hash underscore equals function in PHP that you can use as well. So moving on to number 8, we've got abusing XSLT for practical attacks. Now, XSL is the extensible style sheet language. XSLT stands for XSL transforms, and it's used to transform or manipulate XML documents. So you can have, an XML document come in as input. The output can also be XML. It can also be HTML, a document file, anything. There's 3 real versions of XLST. Version 1 is the most implemented and supported by web browsers. And in this research, he's going to showcase a few precision losses when calculating large sums with XSLT, which is basically going to lead you to know that you should never really use any sensitive cryptographic functions in this. And then also, there is a same origin policy bypass in Safari, as well as a local file read. So we're going to show that right here. Basically, using Safari on Bing.com, you can see in the top right corner, he's authenticated and logged in. His name Fernando. And in the bottom in the exploit browser, accessing private information, he's able to actually pull that value from there using an XLST transform. Furthermore, there is a slightly verbose syntax error when converting these documents. And you can see here what we're actually doing. If you look at the top one, we're declaring the file to access as etc/password, and then doing a value of select document file for that same file that we just specified. And if you're looking at the command prompt there at the bottom, we've got a little syntax error, start tag expected, opening bracket sign, because that's what the start of an XML document should be. And it'll print out that little bit right there as part of the error message. Sadly, there is a character limit on it. I believe it's about 45 to 50 characters. So you can't get more than like the first hash here and something like this. It's not practical to enumerate the whole list. But you can get a little bit of useful information. Moving on to number 7, we have exploiting XML external entities in file parsing technology. There's a lot of surface for exploration here, targeting the OpenXML format, so like .docx, for example, .pptx for PowerPoint, and .xlsx for Excel. And these are all available in Microsoft 2003. They're default in Office 2007, and not pretty much a standard. So each of those file formats, what they pretty much are, it's kind of like a jar file. It's a zip archive that contains many layers, many structures of data, and media files. And throughout those files, what Willow is going to showcase is that you can fuzz for new and different areas of it, that when that file is then uploaded to some popular like file parsing technologies, you'll get a sense of exec callbacks coming back to you, if external entities are enabled. Again, we're flying through this. I know it's a lot of information. Just kind of hang it with me here. Number 6, we have illusory TLS by Alfonso de Gregorio. He presented this at DeepSec last year, or 2 years ago, rather. And this is an instance of the elliptical curve asymmetric backdoor in the RSA key generation. Now, this is going to target a certificate authority, public key certificate, and then you import that in any popular like HTTPS client, TLS server out there. The security outcome here is absolutely the worst possible, because this is going to allow the attacker to impersonate the endpoints because the certificate is trusted. And then you can eavesdrop on communication, do anything of that nature. The problem here is that we often give up trust at the public key infrastructure level. Like say you have like tens to hundreds of CA certs stored in your browser right now. And we're basically trusting that they are authentic. In this particular research, he embeds a backdoor in that. So today, we basically don't have sufficient assurance about all those certificates that may be imported in our browsers that we're using, that they aren't compromised at the source. And the only people that can really detect this is someone with access to the target RSA key generation, or actually, yeah, that's probably it. The susceptibility to detection is also really going to depend on the implementation details here. Very hard to tell if there's an embedded backdoor in this, but it is possible, and we all pretty much blindly trust that certificates are good to go, unless we see that little broken lock icon up there. Number 5, we're going to start getting a little bit deeper here, is abusing content delivery networks with server-side request forgery, Flash, and DNS. So this is by Matt Bryant and Mike Brooks. Now, I normally give this talk to less technical audiences, so bear with me here. I'm going to go over some of the basics. This is how most people think the web works. You know, we're a cat, we ask for an image from Reddit, something, a response comes back. For most people, that's good enough. As we all know, it's not quite that simple. So, you know, in between making requests to the server, you're often going to hit things like load balancers, content delivery networks, various DNS servers. When working on a web app pen test, these are rarely included in part of the actual assessment. So say if you find an issue with one of these things or some sort of scoping problem, what do you do when you're hacking that? You have to like mark it as out of scope, or the client's going to say it's a third party, we don't have access to actually trust that stuff. How many people have ever encountered that? So what do? You just go on with your findings. You continue on with the report. So scoping is probably why an awesome, elegant attack like what I'm about to discuss here hasn't been found yet. Now, in order to exploit this architecture, obviously, you should start by doing a little bit of recon. There's a couple of popular DNS reconnaissance tools out there, like DNS Dumpster, Fierce, DNS Recon. These guys wrote a tool called Subroot. Now, what Subroot is going to do is it's going to enumerate the subdomains through various open resolvers, and even find a few through brute force through side channel attacks, I'll explain here in a moment, to basically give you a way to expand the scope of what can actually all be in your pen test. So let's do a quick background a little bit on some dig records. Quick background on W2 meta queries, actually. So AXFR and any. AXFR is going to transfer the entire zone file from the master name server to the secondary name servers, and any will return all records of all types known to the name server. And if the name server doesn't have any information on the name, obviously the request will then forward it on to the authoritative server. Now, what Subroot can do here, it's a tool that's going to find names, regardless of records, match them, and then recursively crawl through them to find new records. When they ran it against Google, they resulted with over 3,000 records, and just under 2,500 of them were A records. But that's pretty much specifically for Google. You know, they build their own infrastructure. Everything's kind of custom on their end. Type 257 is an emerging standard. It's a SHA-1 fingerprint on the issuing CA cert. So it's a way to prevent malicious certificate authorities from bypassing certificates for whichever hostname is in question. Like, for example, China issuing their own Google certs. And then we have 22 SRV records here, which we'll go to in detail as well. Now, when they enumerated on CNAME records, they found that some of the target subdomains are pointing to Edge Suite, which is one of Akamai's CDN services, which then points by CNAME to an Akamai service, and then points back by an A record to an Akamai server. Now, from there, you can enumerate the SRV records and catch a couple of domain controllers here, like LDAP, XMPP clients, Jabber clients, etc. So then what they did is they used a Subroot tool on an internal pen test and found that they could basically use it to get results the same way through there. So here we have a bunch of LDAP domain controllers. And then the naming convention happens to be a couple of popular hockey teams, like Rangers, Sharks, and Canucks. So on top of that, you can also ask for a record that doesn't exist. And if it doesn't exist, the server is going to say, yeah, this doesn't happen. You get a no error record. If it does exist and you're not supposed to know it, the server's going to say like, hey, I can neither confirm nor deny that's going to be there. So that's your basic CW8203. It's an information disclosure vulnerability, or a timing attack, side channel attack. So using this, you can actually enumerate a list of that by looking for domains that don't exist and record the responses. For most servers, that's going to be a no error refused, or no record found. But if you hit a record that does exist, then you'll be able to discern those two responses to say, hey, okay, this is an actual internal subdomain. So doing this on their internal pen test, we see a couple of things here that are pretty interesting, like internal, dev, what could those be? Okay, if we can just go forward here. There we go. Now, Subroot can also take its output as input, so you can basically cat out the results, grep for no error for strange records, and then rub Subroot on those records. Here, in this example, they found that SCI was its own subdomain under legitbank.com, and obviously we're masking what the actual bank was. We're just going to say legitbank.com for the purpose of this explanation. SCI has its own domain controller found at ldap.sci.legitbank.com, and when you resolve this change, you're going to get an IP address of the LDAP domain controller as an outside attacker. That's key here. So that shouldn't happen. It's an internal address, and in itself is an information disclosure vulnerability, but now we're widening the scope of what we can actually access on this pen test. Now, one thing we might try to do here, if you were able to actually hit the server internally, would be like server-side request forgery. Now, server-side request forgery is all about trust. You know, your server, your target, legitbank.com, might need to trust a virtual private cloud that has services that depends on internal DBs, internal administrative interfaces, internal APIs, things that would otherwise not be accessible. One of the ways that you can legitimately bypass things like the same origin policy would be a cross-domain proxy. And you might find this every now and then if you're actually like working on a pen test. So basically, in this particular example, they found a proxy.php page that took a parameter called CSURL and was pulling back localhost :631. If anyone's familiar with that, that's the cup statement that runs on OS X. And older versions of that, in fact, were actually vulnerable to shell shock. 1.5.3 actually isn't. But this allows you to basically shows that you can break that trust boundary and access a local service from the outside. So what would you do if you were hacking on this? Have it in burp, throw it into intruder, use the cluster bomb attack, and then enumerate through all possible IP address values and all possible port values. What do we find here? So they end up finding basically a Cisco switch on the inside with IP address 192.168.20.1 running on port 80. And I don't have to tell you what the password is, but it's also 5 characters, just like the username is. I'm sure you can figure it out. Again, no one's surprised here. It's kind of sad. So what else can you do? You know, legitbank.com is using a load balancer, and the load balancer here is an Nginx pass-through proxy, and it was routing based on internal host name and passed to internal resources. So what if you try to access one of those domain controllers from earlier? And it's just as simple as like if you were testing in burp, hopefully most people here are familiar with that. You can make a TLS connection to the website, throw it in repeater, and change the value in the host field. So you can see here, they made the initial request to legitbank.com over HTTPS. And now, after changing the request to account.internal.legitbank.com, response actually comes back. So the load balancer was actually passing the connection through to the internal services. So how many people are testing for server-side request forgery on their pen tests? Good. There needs to be more, a whole lot more. Now, do a quick background, just real quick, bear with me here, talk about same origin policy. It's a combination of the port, the scheme, and the domain. And this is going to stop one site from basically requesting information from the other one. So obviously here, like HTTPS, www.example.com can't access the information of a different protocol, a different website. Domains, TLD is the same, but yeah. But JavaScript and Flash act a little bit differently on this. JavaScript is going to execute in the content of the including site's origin, and Flash is going to execute in the context of the hosting site's origin. And if we look at a quick example cross-domain XML file, like what was actually on this pen test here, as we all know, wildcard usage is just way too common. Now, if we combine that with a flow player bypass, which is a popular Swift media tool out there, versions 3.2.16 actually allows you to load plugins from arbitrary domains, meaning you can then source in your own malicious plugin, and then hijack the flow player plugin. 3.2.18 has a couple of integrity checks, but they're quite trivially bypassed. If anyone has a version of flow player on their website, you can basically hijack this way. So now the attack scenario for this particular chain looks like this. The user is going to log into legitbank.com. He's going to then navigate to the attacker page. Then that attacker page is going to load a Swift from the victim site, in this case legitbank.com. That Swift is then hijacked with a custom plugin for it, and then you can perform authenticated requests to legitbank.com. And this all happens because Flash is going to allow you to bypass the same origin policy. Now, we know how to find internal services from the outside using what we just found with subroot. We know that server-side request forgery is possible by design if a bypass proxy exists, which it does in this case. We know that if that particular old version of a Swift is there, we can then load in arbitrary plugins. And the one thing necessary for this is that we're going to need a misconfigured cross-domain XML file, which does in fact exist here. Now, if you're going to exploit this at scale, they wanted to look at content delivery networks. So here's your basic caching mechanism. You have a user, you ask the web, for an image of a cat. Whatever CDN is going to be in place, and this is Akamai Edge Suite, It's going to then make a request to the target server, pull back the image of that cat, cache it, and then anyone that makes subsequent requests to the caching server is going to be rewarded with that image. Now, what if you were able to put a different file there that would then be cached, and other people are going to pull that cached file? That's what they tried doing with this. So this is known as optimization. Basically, in red here, we have a website pointing to Akamai. In blue, there's cache options like time to cache, client ID, things like that. And green is the actual URL. Is that green here? Kind of teal. Akamai's network works by pulling the file off of your server and then hosting it on the CDA. So if you point something like akamai.example.com to Akamai's Edge Suite service, you can then host arbitrary files on the server. But you can only use that site to retrieve them from a certain list of sites. And that site is going to be determined based on what's actually accessible in like the wildcard usage on the crossdomain.xml file if it's improperly configured. So they tried doing this on this particular pen test. So we have the website, the actual bank blurred out here. They were trying to pull back the robots.txt file from Google. Got an access denied message. Wasn't quite expecting that. So let's, instead of running subroot on that thing, let's run it on edgesuite.net, which is what the crossdomain.xml file was allowing for. Lo and behold, this is what they found. A repository of all versions of FlowPlayer, including the ones before 3.2.16. Okay, so now we can host in our arbitrary plugins, and we have a chained attack as follows. So as the attacker, we're going to force them to visit our page, which is going to then make a request to a Swift that we're loading an arbitrary plugin from, which is going to then allow us to access things that are inside that crossdomain.xml file, which would be legitbank.com. At scale. So this is going to be happening through the CDN. Moving on to 4, we have evading all WAF cross-site scripting filters. And I say all here in asterisks because it wasn't really all of them. It was really just more like the 6 major ones with major browsers here. But one important takeaway that you all have to realize when I go through these slides here is how simple these injections are. And these are working on current modern day WAFs. If anyone here is in the bug bounty scene or wants to get a couple quick bug bounties on WAF vendors, I feel like they're ripe for the taking because these bypasses that get through are sort of laughable, and these are products that are actually selling. So here's on F5, big IP WAF, your basic body style, height is some value, then on wheel something. That's all it took to get through. Div context menu, XSS, so when you right click on the menu, the context menu happens, and then the on-show event handler will get through. When you see things like this, it makes you wonder if they're even trying. This is my perspective as a hacker, so I kind of laugh at this just a little bit. The other body style one, so just a little quick URL encoding, we'll get you through on that one. On the very last one here, they're just taking like one character in the prompt one, HTML entity encoding it, URL encoding it, and then that gets through. And then, so when these findings were reported to the F5 security team, they acknowledged the findings, stated that an update would be available in September to patch the issues, and then in fact they were. Now for Imperva and Capsula, this might look a little weird with all the coloring. It's best to read it from the bottom going up. So all they're doing here is, a Unicode encoded P, and then each of those characters there, the parentheses, the single tick, the XSS, they're just HTML entity encoded, and then URL encoded one layer above that, and then double URL encoded again above that. So all this stuff gets through Imperva. Their team was pretty quick about patching the findings. But this is not really that difficult stuff. It's really just a series of various encodings. It kind of reaffirms you to the fact that WAFs are not the answer. They are a slight Band-Aid. They'll help you in the meantime, but you still have to do all the proper input validation and output encodings on your server. AQtronics WebNight, something as simple as detail on toggle will work. Again, quite trivial. I hear a couple of people giggling. For Barracuda, the same thing, copy and paste injection, body style, on wheel. These are current versions of these WAFs. Nothing elegant about this stuff. PHP IDS, the only difference here is that this is tailored for a GET request, where the plus side is going to be a delimiter for spaces. So SVG on load equals, and then some injection, no problem. Mod security, I feel, is one of the better WAFs out there. They have an awesome community behind it. They're updated quite quickly. There is a form, one of my more favorite proof of concepts is that you can put ampersand tab semicolon and ampersand new line semicolon in between the character's JavaScript when you're firing from a JavaScript URI. And the only way that this bypassed the mod security one was when 785 bytes or more of those tablatures were in basically in the injection. So it's probably not going to work over a GET request because the URL is going to be too long. The server limit's going to not allow that to go through. But in a POST request, no problem. Number 2 is US ASCII encoding, and that's basically a malformed ASCII 7 bits instead of 8. And then for number 3 here, it's just a regular, some tag on mouse over alert, URL encoded several times. Quick defense, just input type search on search equals alert, details on toggle alert with a Unicode encoding. Quick defense did say that they are in active development and not currently, this is not meant for production. I'm not sure if it was actually fixed in a timely manner or not, but they've got some promising research coming forward. SecureEye, same thing, same US 7-bit malformed ASCII encoding. Not that difficult stuff, right? Like none of those injections were really too crazy. It's a little bit of encoding stuff or a little bit of obfuscation, but really not anything too crazy. Most of this stuff is all in the HTML5 security cheat sheet. If you want to go for some bug bounties, just target the WASP vendors. I'm pretty sure they're just open season. Number 3, this is going to get a little cooler. We've got web timing attacks made practical. There's not a lot of real good practical timing attacks research out there for websites, aside from this one particular tool called Racer, which I'm going to go over in a moment. So they set out to do a couple of things here, and a lot that was mainly make the research a little bit more elegant, find a new way to attack this stuff, and create an automated tool that could actually determine if a timing attack exists. One of the natural problems there is that how many requests do you have to actually make to discern that a timing attack is there, especially if you're crawling through many things on a website. It could be 100, 100,000, 100 million. At some point, it just gets a little too impractical. So trivial example of a timing attack. Let's just say you're trying to log into a website, and you use the login admin and the password, just some random characters, something you know is going to fail. And you get a response in maybe 1 millisecond saying, login incorrect or something like that. And then you try logging in with something else with a known username that is not correct. So you just type on the keyboard a couple times, another known password, something you know is going to fail. And you get a response time in, say, 200 milliseconds. If you do that, if that works on the website, you can then enumerate through and basically evaluate the response times to develop a list of all known login, or like usernames. If that happens to be the variant of an email address, you can data mine an email address that way. These are typically a little bit more difficult to defend, but you can normally deduce some real information out of it. So this is really most of the research that's done so far. There's cache timing attack on AES in 2005, cache missing for fun and profit by Percival, and then the Lucky 13 attack, which was actually one of the top 10 web hacks, not last year, maybe 2 years ago. But what about web hacks? Most of the research is limited to specific vulnerabilities. They're only tested under synthetic network conditions. Time trial, Racer are 2 tools that come to mind for this, and statistical analysis can probably be really improved on this. For instance, with the Lucky 13 attack, I think the most intense math on that done was like medians, just averages. Now, previous researchers here actually left the thought of using TCP timestamps as more as an open question about making attacks more efficient, and that's what Dan Morgan here wanted to, or not Dan Morgan, Timothy Morgan, excuse me, wanted to do here. So, on to TCP timestamps. They're a simple mechanism to make TCP checking more efficient. Basically, when a host sends a packet, the current time is actually sent on the packet and eliminates noise. You see it in every header, it's RFC 1323. And this is when you're doing this, you're actually analyzing data at the packet level. So you have to be able to work out complex issues like the retransmission of packets, dropped packets, if packets come out of order. You need to be able to address all these things so you can evaluate the true round trip time of the packet. And at the end of the day, after working with TCP timestamps, they weren't able to use them directly to measure timing differences with any real accuracy, but there's information that's useful when paired with other timing attack data, which we're going to go into. And it kind of forces you down this path of packet analysis, of actually analyzing the packets as they come and go from the network card, which ends up making the timing measurements much better. Because in other cases, with past research, let me get on here. So like for instance, here's a typical HTTP packet. And if you look at your very simple HTTP request, and you're trying to measure the round trip time here, you've got many things going on. You've got the open connection, the sending of the data, measuring the time you sent it, measuring the time you received it. When all that's going on, what you're actually measuring is the time that it takes for the data to be sent through the kernel, the time that it takes to get on the network card, the time that it takes for then a TCP handshake to commence, the time it takes for a receiving kernel to receive the response, then it has to get sent back all the way back to the user space application. Then your kernel eventually will schedule the user space back onto the CPU. And so there's a lot of variance there that we really want to eliminate in order to get really good measurements here. Simply, that can be done with evaluating the TCP timestamps. So if you can see here, we've got Racer on the right, which is measuring stuff in user space like what I just described, versus Nanone on the left. And you can see that this distribution is a little bit prettier. It's a little bit more narrow there, which is good. That's more accuracy. It's a smaller thing. And then looking at the median of the absolute deviation of these two distributions, which is a measure of variance, it's about 40% less. Now, when you look at the data for one of their research mechanisms a little bit more like a function of time of day, it looks kind of like this. So it's a scatter plot here. You can see right below the blue there's a bunch of red dots, and that's one of the requests. Blue is the other one. Basically what you see is that early in their test, all of their responses were coming back quite fast, and then somewhere right after it started, everything got longer. And they're doing this test over the web, so there's various noise interference there. But it's all still quite similar to each other, quite relative. And what they believe happened here, is anyone familiar with Comcast in the US? Yeah, so hashtag Comcast. Basically what they do is they give you really nice speeds at first, and then once they see you're using a service, they throttle it down. So here we've got some new variants in the data. But when you do like a pairwise sampling of that and just the differences of those times, you then get the purple graph down here, which is a lot more uniform. And 1 second. Yeah. So that's the difference between each time pair measurement. And if you can do this around a central tendency, you can measure the location of that central tendency, meaning what is the average distance between the two requests. You can then decide if it's like a 0 or non-zero. If it's 0, there's a timing difference. If it's not, there isn't. And that's one new methodology on how they approach this problem that hasn't been done yet. So they then created this tool called Nanone, which is in active development right now. What they're trying to measure is risk and how much risk is in place for a particular timing attack. It's in, like I said, it's in active development. It's not finished fully. It's also not really easy to use. You have to be very comfortable in the command line with editing it yourself. But the goal here is to basically have a stronger way to evaluate if a timing attack does exist. Now, avoidance here, to stop timing attacks from happening, one simple request, which is an easy cop-out, is say put a captcha on the form. As we all here know, they're easily defeated. And it's really easy to just say, code this in a way such to where no timing differences are discerned. So that it takes the same amount of time, but we all know that's tricky. Even if the code is compiled, oftentimes the compiler will reorder certain machine instructions to make it more efficient. So you could be evaluating everything on the source code layer and then observe something completely different when you're actually assessing it. So basically it tells you that you have to do constant assessments to make sure that this doesn't happen in the real world. Moving on to number 2, we have logjam. So we're getting back into a little bit of the encryption realms, which have won the top 10 webpacks in the past years. So logjam, explained simply, it's a downgrade attack. And it's a downgrade attack that targets the Diffie-Hellman key negotiation. So basically, you just have an attacker man in the middling asking for a downgrade attack. And then one difference about this between Freak is that these responses have to then be cracked in real time. So you have a lot of, say, Diffie-Hellman 512 keys that the attacker is going to pre-compute. There's not a large scale of what those actual values could be, so it's very easy to build a huge list of what it is. You man in the middle someone, you force a downgrade to happen, and then when the response comes back, you just crack it in real time. And it's really not that hard to do. Most keys out there are Diffie-Hellman 512. It takes moderate resources to crack that. Nation states can likely crack 1024 bits. And fix is quite easy, actually. If you're still using the DHE export cipher, you just have to up the bits to 2048. Else, just simply disable them, as we often do for outdated TLS libraries. And if you're a system admin or a dev, just upgrade your services. If there's one quick fix to any problem you might have, it's just constant updating. And then moving on to number 1, we have the Freak attack, which is the factoring attack on RSA export keys. It is just as simple as the other one. It's a downgrade attack where the attacker gets in the middle, man in the middle style, but he asks for export grade RSA encryption. Now, what we've learned here with this top 10 hacks this year is that branding is still very prevalent. Going from like shell shock to bash drawer, freak, crime, beast. We have branding left and right on all the hacks. SSL and TLS targets are still highly targeted. The research is very appreciated, and web security prevails. In this day and age, I'm fairly certain if it's not the ransomware side of the world, people aren't really looking for your My Documents folder anymore. They want your Gmail, your Facebook, that kind of stuff. And then, special thanks to the researchers and the experts that helped us track this list down. Like I said, this is a different list than what you're probably going to see elsewhere. There's not a company with an agenda or anything ordering them in a certain way. This is what was chosen by the InfoSec community and by the people that favor that kind of research. So not only do I want to say thank you to the experts, but thank you to everyone that put forth research for this. This is supposed to pay homage to those people that are doing awesome and wonderful things for the InfoSec community. And we'll be doing this list again next year. If you happen to be working on research yourself, feel free to nominate yourself. If you know someone working on something awesome, feel free to nominate them. And then hopefully we can see you guys on this next year. Thank you.
Okay, questions?
If there's no questions, I'll be floating around the conference. Feel free to just grab me at any point.
If you go outside, I would like to remind you to vote on the call, green or red. Thank you.